So let's pick up at the ideal gas law. Previous to this slide, we talked about how different properties that we can measure, such as pressure, volume, and temperature, how all of those different um, quantities that we can measure of a gas sample, how they are related to one another. So if you change one, how does another property, physical property change? So now the last quantity that we talked about with measuring a gas sample includes quantity or number of moles of a substance. And so this is where the ideal gas law comes into play because in this previous slide we talked about how where is it that we saw that with all using all of the different laws and relationships that pressure times volume over temperature is equal to some type of constant. So what we're going to do is actually just move this temperature property over onto the other side. And what this constant actually is related to the number of moles of a sample. Where am I? Right here. And that is essentially what the ideal gas law is. We have pressure times volume is equal to the number of moles in a sample times the ideal gas constant R times temperature. So when we're talking about one sample and changing its environment, changing its pressure, its temperature, this N times R stays constant um, when you have the same sample that you're just moving into different environments. So stays constant with different samples. All right, so NR is that constant K that we talked about previously. So N is number of moles, and R is our gas constant, which is this value. So there's actually a lot of different values for R, but the one that we will use for the ideal gas law is this one, 0.08206 liter ATM over mole Kelvin. So it's very important that when you input different units for our pressure, volume, and temperature, that it matches what unit is in our R. All right. Oh yeah. So always use matching units in ideal gas law calculation. So if you want to input a pressure, always have it in ATM because if you want to use this R constant, it has to cancel out with this the unit associated with this R. And it's easier to just convert all of these quantities than to memorize like 10 different types of R that have the units that you want. It's easier to just change these different quantities into the unit of this R. All right, so pressure typically expressed in ATM, volume in liters, and temperature must be in Kelvin. And then obviously quantities will be in moles. So I think if this next slide, let's just go continue on. So what is the ideal gas law? So it's essentially we're saying that we're describing a gas sample and saying that is ideal. So an ideal gas is just a theoretical gas that obeys the ideal gas equation under all conditions. So in real life, gases are closely follow the ideal gas law equation at low pressures and high temperatures. So at earthly conditions. So on Earth, in real life, gases do follow the ideal gas equation pretty well because we're at low pressure. 1 ATM is considered low pressure, and we're at fairly high temperatures. So these earthly conditions make it so gases follow the ideal gas equation. For the most part, when doing questions, if I talk about gases, assume that they're ideal, unless I say otherwise. If I say, treat this substance as a real gas, which we will get to the end of this chapter. But otherwise, just assume all gases are ideal. All right, so the ideal gas law written here. So if you remember the combined gas law that we had previously in a couple slides back, the combined gas law equation and the relationships between P, V, and T, it all comes from the ideal gas law. So you don't actually have to memorize a bunch of different equations and a bunch of different relationships because this equation tells you everything. So like let's remember Boyle's law. It said that pressure and volume are inversely related to one another at a constant temperature. So if you look at the ideal gas law, it tells you that. So it says at a constant temperature. So at a constant temperature means that this side of the equation stays constant. All right? And so we're only changing P P and V here. So if pressure goes up, ooh, this is being kind of laggy. If pressure goes up, volume, in order for this side of the equation to stay constant, volume must go down in order to maintain that relationship, in order to maintain this constant on the right side. So, pressure goes up, then volume makes up for it by going down. Or pressure goes down, then volume has to make up for it by going up in order to maintain that balance. All right, so that's Boyle's law. So, or if we look at Charles' law, volume and temperature are directly proportional to one another. So you can just think, okay, if volume goes up, but pressure stays the same, if volume goes up, we also, in order for this equality, it to equal one another, temperature also must go up. If volume goes down, then temperature also must go down. All right, so it's all right there. And so this really isn't another equation that you have to memorize. It all comes from the same equation. It all comes actually from the ideal gas law. So the combined gas laws that we saw earlier, we just have to rearrange the ideal gas law. So if we have two instances, this is two instances of the ideal gas law, two instances. So this is like the sample at one type of condition, and then here's the sample at a second type of condition, or something like that, right? So NR, we said, stays constant. This is constant with the same sample. Same sample. So if you just rearrange sample, if you just rearrange things, so I can say P1 V1 over T1 equals NR, P2 V2 over T2 also equals NR. I can set these two equations equal to one another because they're both equal to NR, all right? And so then out of that you get the combined gas law. Combined gas laws. All right? So you can see it right here that we have, one side of the combined gas law and then the other side of the combined gas law. And then from that, you can get all of the rest of the named gas laws from the combined gas law, depending on what the question is, depending on what is staying constant. So all of this comes from the ideal gas law. So if you are to memorize one, memorize PIV-NERT. PV equals nRT, or PIV-NERT. All right, so let's just do a couple questions to get our gears lubed up for gas law questions. So here's a question. How many moles of gas are there in a 45-liter container at 80 degrees Celsius if the container displays an internal temperature of 500 millimeters of mercury? So I'll just go through and kind of identify all the numbers that they give us, because I know that I'm going to have to use it in the equation somehow. So moles, I know that's a type of unit. Moles, that's N. How many moles are in 4.45 liters? So I know that's a volume. At 800 Celsius, there's our temperature, displays internal pressure of 500 millimeters of mercury. That is a pressure. So if I take our PIV-NERT equation, let's just kind of take inventory of what we have. Okay, so they gave us a pressure. They gave us a volume. They gave us a temperature. R is a constant, so we know that. So we need to solve for N, our number of moles. But remember what units things have to be in. So R, the unit of R is 0.08206. Is that right? Liter, ATM, mole, K. So I need all the units that we put into the equation. So volume needs to be in liter, which it is, so we're good there. Temperature needs to be in Kelvin, but we're in Celsius, so we'll have to change that. And then pressure needs to be in ATM, but we're in millimeters of mercury. So I need to change those units. All right, so I can just do this all in one step. Since I know that we're solving for moles, let's just rearrange our equation. So PV over RT. All right, so pressure, 500 torr, but I need to get that into ATM. So I can say 500.0 millimeters of mercury is 760 millimeters of mercury. All right, that is an ATM. Our volume is 45.0 liters. That's good. R is 0.08206 liter. atm mole Kelvin. And then temperature, they gave it to us in Celsius, so 80.0 plus 273.15. So that will give us it in Kelvin. And so you just plug that into your calculator and you should get an answer of N equals 1.02 moles of what? Let's just kind of define. So moles of, oh, it doesn't actually say what kind of gas it is. It just says a mole of gas. So moles of a gas will occupy 45 liters at 500 millimeters of mercury pressure and 80 degrees Celsius. Let's just check sig figs here. So pressure has 4, volume has 3, and here Celsius, our temperature has 3, but because it's addition, this actually has 4 sig figs, so we're actually limited by 3 sig figs here in our volume. All right, and so that's why I have 3 in the answer. All right, so there's one more question. It says your turn, but let's just do it anyway. Assuming ideal gas behavior, what volume will be occupied by 115 grams of methane at 3.5 atm and 25 degrees Celsius? So let's just write down our equation again and take inventory. So pressure, where's our pressure? Okay, good. So they give us 3.5 atm. We have that. Great. All right. Temperature, we have temperature here. All right, but we need to convert that because it's in Celsius. We want it in Kelvin. It's asking for volume, so I want to figure out volume. Do we have moles? Well, they give us the mass and the mass of the gas and the molar mass of the gas as well. So since we know the amount in grams of the gas that is in this container, we can use the molar mass to get the number of moles. So we need to convert 2 different things, temperature and moles here of gas. So let's just do that first. So I'm going to figure out our number of moles. If I have 115 grams of CH4 methane and use its molar mass, grams of methane is 1 mole of methane CH4. That equals something. It equals 7.1696 moles. I know I have too many sig figs here, but that's okay. I don't want to introduce rounding error. So 115 grams of methane is also 7.17 moles of methane. So this is our N. This is what we will put into our Pivnert equation. So what are we solving for? Volume. So let's just rearrange our equation. So I isolate volume. So V equals nRT over P. So, okay, N we just got, so 7.1696 moles. R is 0.08206. I will always give you R, by the way. Liter ATM mole. Okay, but it's up to you to know how to use it. All right, temperature, what is it? 25 degrees Celsius, but we need that in Kelvin. So 25 plus 273, 0.15, that would be in Kelvin. Over pressure, which is 3.50 atm. So, let's just check our units here. So moles cancel out with moles in R. Liter can't, oh no, I think we're left with liters at the end. ATM cancels with ATM. K cancels with K. So we are left with a liter unit. All right, and so if you do this, you get that, plug that into your calculator, you get that the answer is 50.1 liters. We are limited by the 3 sig figs in our, a different color. 3 sig figs in our pressure, and also 3 sig figs in our temperature. Although it gives us 25 because we converted it to Kelvin, so this is actually 298 Kelvin with 3 sig figs there. All right. Oh, and I think everything has 3 sig figs. Okay, great. So let's look at another way we can use the ideal gas law to answer some questions. And so I need to come up with a couple definitions for you, and that is what STP, or standard temperature and pressure, is, and what molar gas volume is. So we can relate the number of moles of a gas that's present to the volume that it actually occupies. So we're essentially relating, the N component of the ideal gas law to the V component of the ideal gas law. But in order to make this relationship, we have to know what the pressure and the temperature of the environment is. All right, so just a couple definitions. So, it's often convenient to define molar gas volume. So essentially, this value is the volume occupied by 1 mole of gas at a certain given temperature and pressure. And so a common temperature and pressure that chemists and scientists use is called STP, or standard temperature and pressure. And that is defined as 0 degrees Celsius. So this is our temperature component, and 1 atm. So that's our pressure component. So, if we remember PV equals nRT, in order to define molar gas volume, that says, 1 mole, what volume does 1 mole occupy? We have to know what T and P are as well. And so standard temperature and pressure, STP, can define that for us. And so the standard gas volume for 1 mole of gas at STP is 22.4 liters. So in high school, when you talked about gases and maybe the ideal gas law, this number might sound familiar to you. It said 1 mole of gas is equal to 22.4 liters. But that is only true at STP. So at STP. So essentially, to get this value, all you have to do is plug in the values of STP into PivNert. So all you have to do is put 1 atm, volume, so just calculate for volume equals 1 mole, because we want to know how much volume does 1 mole take up, R, whatever that is, and then temperature, which is 0 degrees Celsius, so 273 15 degrees Kelvin. So if you just plug that in and solve for V, you will get our STP volume. If you did this same equation, but at room temperature, so if we change the temperature from 0 to actually 25 degrees, which is closer to the gases you and I interact with on an everyday basis, it changes a little bit. So the molar gas volume will change to 24.4, and that's if you change this temperature to 25. I think it's 298 degrees Kelvin, which is 25 degrees Celsius. All right. Okay, so how else can we apply the ideal gas law? So one way I can ask you a question that involves the ideal gas law is to ask for a molar mass of a pure gas using the ideal gas law. So we can rearrange the ideal gas law if we know the mass of our sample and its pressure, volume, and temperature. And we can get this because we know that the molar mass and moles are related to the total mass of the sample. So I know that the number of moles in a sample, moles of gas in a sample, is equal to the mass of the sample over the molar mass of the substance. So if it was like methane, CH4, you could weigh the sample, you can figure out what the molar mass of CH4 is, which is like about 16 grams per mole, and then you can get the moles of the sample that way. Or we can kind of reverse, or not reverse, but we can leave out different portions of this relationship, and instead of you needing to figure out how many moles of gas is in the sample, maybe I will tell you how many moles of gas are in the sample by giving you the elements of PivNert, and the mass of the sample. You can then calculate the molar mass of the substance. So let's just shorten mass of sample as M and molar mass as capital M. So if I rearrange, little m over m is equal to n number of moles. So essentially, I'm just inserting that into, it's a little bit offset, I'm sorry. You just stick that into our PivNert equation in place of our n component, all right? And then just rearrange for big M molar mass. And you get that the molar mass is equal to the mass of the sample times R times T over PV. And we were able to do this by utilizing the n component, the number of mole component in PivNert. We also must know the mass of the sample. So in order to do this, we must know the mass of the sample and the formula of the sample. So like what substance is it? Formula of substance. So is it CH4? Is it NH3? Is it H2? Is it N2? You know, something like that. All right, so let's just do a sample question. So we have a sample of gas with a mass of 22, 51 grams, and occupies a volume of 120 milliliters. The sample displays a pressure of 748 millimeters of mercury at 80 degrees Celsius. Oh, I guess we don't have to know it. So depending on what we're solving for, this should say we must know mass of sample or formula of substance to get the molar mass. That's what I meant. All right, sorry. Okay, back to this. Okay, so we're given all these things. What's the molar mass of the gas? So let's just take the formula from the previous slide. So molar mass, big M, is equal to mass of the sample times RT over PV. So we are still just using just a different iteration of the ideal gas law. So make sure that all of our units that we insert into this equation match R. So we have mass of sample. The volume of the sample is in milliliters, so we need to change that. And the pressure is in millimeters of mercury, so we need to change that. And the temperature is in Celsius, so we also need to change that. So keep all those things in mind. So I'm just going to do this all in one step. So mass, 0.2251 grams times R, 0.08206 liter ATM, liter ATM mole Kelvin. Temperature is 80 degrees Celsius, but we need that to be in Kelvin, 273.15 Kelvin. Pressure is 748 millimeters of mercury. So divide that by 760 to get ATM. And then volume, man, I have to change everything. 120 milliliters. We need to get that to liters. Okay, so if you plug all of that into your calculator, you should get an answer of 55, big M equals 55.2 grams per mole. So let's just look at sig figs here. So mass has 4 sig figs. So it was at 80, yeah. So 80. So this has 3. Our temperature has 3 sig figs. Our pressure also has 3 sig figs. All right, and our volume has 4. So we're limited by 3 sig figs here. So our answer should have 3 sig figs. Let's just check units here so you can believe me that this all works out and we get grams per mole. So grams. All right, so liter cancels out with the liter down here, and we canceled out our milliliters there. Pressure, millimeters of mercury cancels. ATM also cancels with part of R. Temperature cancels here. And so now you see that we're left with grams per mole on the bottom there. And that's what gives us our molar mass. All right, so let's do a different type of iteration of the ideal gas law. And so this is a different way you can apply our favorite Pivnert equation. I'll just put it into the corner so we always remember it. And that is determining the density of a gas. Remember, gases are much, much less than the density of liquids and solids. You know, I always, keep in mind like the density of water is 1 gram per milliliter. A gas typically is measured in grams per liter. So, like a couple grams of weight, but now in this much, much larger volume. So gases are much less dense. So again, so let's try to get a grams per liter type unit going on, starting with the ideal gas law. So I have that here. So if I want density, I know that density of a substance is equal to its mass, the mass of a sample. So of a sample over the volume of that sample. So cool, I have one of those. I have one of those components in the ideal gas law. We have this volume component. There's a volume component in the ideal gas law. That's great. So what about this mass component? Well, we know that mass is related to the number of moles of a substance. So again, if we relate that back to the equation previously that we used, that the number of moles of a sample is equal to the mass of the sample over its molar mass, we can use both of those equations to basically get density and combine them. So essentially what we're going to do is say that we're going to rearrange our density equation to rearrange our density equation to put mass on one side. All right, so mass is equal to density times volume. And then we can put that into our N equation, because this is going to go into our ideal gas law. All right, so then we're essentially sticking this first equation into this equation, into the N number of moles equation. And then so we can stick that right into our PV equals nRT. Where is that? So it's density, it's this. So we stuck that into our ideal gas law. And then you can rearrange some things, and you see that actually volumes cancel on each side, and then that you get that using the ideal gas law equation, you get that the density is equal to the pressure of the sample times the molar mass over R over T. And so always, again, keep in mind the units that are expressed here, that because of the unit of R, it's in a liter, that our density will be expressed in grams per liter. Or sorry, yeah, grams per liter, not grams per milliliter like in our solids and liquids that you're used to. Okay, so let's do an example. Let's find the density of ammonia gas, NH3, in a container that's 4.5 liters at 885 millimeters of mercury pressure and 52 degrees Celsius. So almost everything needs to be converted. Let's start with the equation, density equation, because we are trying to get density, so we need to get the density equation. But you can always just formulate the density equation using the ideal gas law yourself by using this, the equation for density that you know, the equation for the moles that you know, and the ideal gas law equation. So if you combine these three equations, you can get density out, and that's essentially what we just did. So density equals, what is it? P, pressure, molar mass, over RT. Is that right? Yep. Okay. So I'm going to just do this all in one step. But remember, our units need to reflect that of our ideal gas law. Or sorry, our ideal gas constant. So pressure is 885 millimeters of mercury. Need to get that into ATM. It's an ATM. So molar mass, this is of ammonia. So ammonia is what, 14? Yeah, 14.01 plus 3 times 1.008. All right, so the molar mass of ammonia is, I have it here, 17.031 grams per mole is the molar mass of ammonia, NH3. Okay, so I have pressure here. Now I need my molar mass, which is our 17.031 grams per mole, over R, which is 0.08206 liter.atm, over mole dot K, times our temperature. So what is this? 52 degrees Celsius plus 273.15, and that's at Kelvin. All right, so just stick that into your calculator, and you should get 0.743 grams per liter. Let's check units. So unit-wise, our pressures cancel, our moles cancel, and our temperature cancels. So you can see that we're left with a gram and a liter down here. And so that's grams per liter. That's our density that we need. Also, let's take a look at sig figs. So our favorite. So 3 sig figs for pressure. Since molar mass we just looked up, and there's plenty of sig figs on the periodic table. We don't have to worry about that. So then temperature has 2 sig figs here, but because we're converting to Kelvin and we're adding it to 273, this actually has 3 sig figs. So yeah, our answer is going to have three sig figs. Okay, great. So let's start talking about mixtures of gases. So we're much more likely to work with mixtures of gases here on Earth in earthly conditions. So one of the most common mixtures that you might think of when it comes to gases is the air that we breathe. You know, it's not actually pure oxygen that we breathe. It's a mixture of many different gases. It's mostly diatomic nitrogen. So almost 80% nitrogen. So I have that here. And then it's about 20% oxygen that we need to breathe. And then almost like less than 1% is other gases. And so that is mostly argon, is that 1%, plus a lot of other really small components of other gases such as CO2, methane, water vapor, which is, is still a gas. So water just in the gas phase, and other pollutants in the air. And that makes up less than 1%. So mostly nitrogen and oxygen. So we can study the individual gases, like we have been doing in using the ideal gas law, looking at pure gases of just individual substances, or we can study these mixtures. And so that brings to question this new definition of, okay, how does the pressure differ when we have a mixture of gases present in a sample? Because I can blow up a balloon filled with my breath, which now we know is actually a mixture of gases. I can blow up that balloon, and that balloon will have a certain pressure associated with it, right? But I know that there's different components of gases in that balloon. So how do those pressures stand up? And so that brings up the concept of partial pressures. So a partial pressure is just the pressure a particular gas within a certain mixture would exert if it was the only gas present. So if I had a balloon that was 1 atm, a balloon and the pressure inside it was 1 atm, and it was filled with air, the air that we breathe, that 1 atm is the combination of all of the partial pressures of all of these different things in it. All of those partial pressures would add up to the pressure total pressure we measure, which is 1 atm. All right, and so let's talk about how we calculate partial pressures in gas mixture. So again, the total pressure, or P, see it's P sub T, so that just means total of a mixture, is just the sum of all the partial pressures of the components of the gas. So it's really important that we know the mole percent of the different components. So like here, where I have the different percentages, these are mole percents of the air that we breathe. And so here are just equations expressing that the pressure of the total pressure of the sample is equal to the sum of all of the partial pressures of the components. Or you can express it like this. All right, so if there's 3 components of the system, then you have to add up all 3 partial pressure components to get your total pressure. All right, so you can also express the partial pressures in terms of mole fraction. So it's essentially just the percentage of each of the different components. And so a mole fraction is just this fancy looking X. That's the sign we use that just means mole fraction for a particular gas in a mixture is given by the moles of that gas divided by the total number of moles. So it's essentially like its percent composition, but in terms of moles. Where you take so if I have a substance I, if I know the number of moles of I that is in a certain mixture, and then I know the total number of moles in that mixture, then I can get the mole fraction associated with that substance I. And so what that means is that the mole fraction of that substance is also related to its partial pressure. So what this equation is saying is that the partial pressure of that substance is equal to its mole fraction times the pressure, the total pressure of the whole mixture, the whole sample. So the ideal gas law, that's the ideal gas law, that's what that should say, works with partial pressures and moles of like one component of the sample. It also works with total pressures and total moles present in a sample. So I think we'll do an example here. So here a mixture contains 11.2 grams of ozone. and 14.4 grams of nitrogen gas. If the total pressure of this mixture is 721 millimeters of mercury at 10 degrees Celsius, what is the volume of the container, and what are the partial pressures of the two gases? So you can just think, okay, I have a container, all right? It has O3 and N2 in it, right? There's a certain total pressure associated with this, and it's the sum of the pressures exerted by both the ozone and by nitrogen gas. And so that P total they actually give us here is, so here it says if the total pressure of this mixture is 721 millimeters of mercury at 10 degrees Celsius, that is our P total. So 720, that's the pressure of the entire sample, right? And so it wants to know what is the volume of the container and the partial pressures. So I would say, since we're using the ideal gas law, PV equals nRT, we need to know the number of moles of each gas. I know pressure, we want to know volume, we know temperature, we need to know N, but they didn't give us N, they gave us grams. So let's just convert those substances into grams, or sorry, from grams to moles. So let's do that. Where am I in my notes? Okay, so the N, so let's do it separately first. So the N, the number of moles of ozone is equal to the mass of ozone sample divided by its molar mass. So I think I have it here. So it's 48 grams is 1 mole of ozone. So that equals 0.233 moles of ozone. All right, so do the same thing for the other gas present, which is N2. So there's 14.4 grams of N2. Use the molar mass of N2. There's two of them, so it's 28.01 grams per 1 mole of N2. And so the number of moles of nitrogen there is 0.514 moles of N2. So these are just partial amounts of moles contributing to the total number of moles. So we can calculate the total number of moles in the sample. Total number of moles in sample is just equal to our N of our two components in here. So you just add up our moles of ozone and moles of nitrogen. And then so that will equal 0.233 plus 0.514. So our total number of moles is 0.747 moles of gas is present in this sample. So this number is, we can use this and relate it using PivNert. So our P total, so this is equal to N total sub T. So it's the total number of moles of the sample. So we can use this equation. So our total pressure times volume of the container equals the total number of moles times R times T. So just make sure, so we get total pressure because we're taking into account the total number of moles. We couldn't do this unless we knew the total number of moles, meaning that we had to convert grams to moles for both of the substances and add them up. All right, so we can use this equation to get, we're setting up this equation. We can do this because it's total moles sample. We're using like the total moles or the total of the sample. What are we actually calculating for? We need to, what is the volume of the container? So because both components, ozone and diatomic nitrogen, take up the entire container, and that is what constitutes the total pressure, we can calculate the volume of the container because we know the total pressure of the entire sample. So we know P total, we know N total because we just calculated it, and we know temperature. So we're solving for V here. So V equals NTR, temperature over pressure total. All right, and so let's plug those things in. So it's 0.747 moles of total gas times R, which is 0.08206 liter ATM over mole Kelvin. I'm just going to skip that part. Temperature is 10 degrees Celsius, so 10 plus 273.15 Kelvin over pressure total, which is what, 721. So 721 millimeters of mercury, but we need that to be an ATM, so 760 millimeters of mercury. That will give us ATM. So if you stick that into your calculator, you should get that the volume equals 18.3 liters. Great. Okay. So we got the first part of the question. What is the volume of the container? Now the second part of the question says, what are the partial pressure of the two gases? All right. So we know the number of moles of each of the gases, and we know the total number of moles of each of the gases. So we'll be able to get our mole fractions pretty easily. All right. So to get the partial pressures, we need the moles of each component. Okay. We need total moles of gas, and we need to know the pressure total, which they gave us. All right, and then so all we have to do is multiply the mole fractions of the two different components to total pressure, and we'll get it. So let's just remember what that equation is. It is our partial pressure. This is partial pressure of a component. So I'll just take away the component part. Let's just pretend we're doing it for one of them. So our partial pressure for ozone is equal to the mole fraction of ozone times the total pressure. So in order to get mole fraction of ozone, we need the number of moles of ozone over total number of moles. All right? And so if we could just rearrange some stuff to help us. So partial pressure of ozone is equal to what? Moles of ozone over total moles times total pressure. Great. So now we have an equation. And we know all of these values, so we can just plug it in and get it. So we have to do it for both ozone and nitrogen. So let's do that. So for I'm just going to copy it because I'm kind of lazy. All right, so there's our equation for ozone. And then our equation for nitrogen is the same thing, but obviously the numbers for nitrogen, but the P total stays the same. So, okay, so what values do we insert here? I think I have it in front of me. So for ozone, it'll be 0.233 moles of ozone over total moles, which is 0.747 moles of gas times our total pressure, which they gave us. Let's just stay in millimeters of mercury because the question didn't tell me what unit to put it in. So you see that, if we did this equation and looked at our units, moles cancels from our mole fraction. The mole fraction doesn't have a unit because it's just literally a fraction. It's the number of moles of a certain component over total number of moles times pressure. So our unit will be left in millimeters of mercury. But I'll write out the other equation too. So 0.514 moles of nitrogen over total number of moles, 47 moles, times 721, our total pressure. All right, and so, okay, lagging there. That is our total pressure, so you just plug that into your calculator, and the answers you should get are 225 millimeters of mercury and 496 millimeters of mercury. And you'll also see that I also did not have to do this second equation here to get the second partial pressure because these two values add up. It adds up to P total. It adds up to 721. So once I got one, you could just subtract it and get the other if you wanted to. So that's another way that you can calculate that. So the equation for that would be P total for this specific question is P partial pressure of ozone plus the partial pressure of nitrogen. Nitrogen is equal to the total pressure of the whole system. So once we did this once, you only have to do it once. You can, since we know P total, you can calculate for the partial pressure of nitrogen. Okay. All right. So the last so now we're kind of like building on difficulty with using the ideal gas law and how I can ask a question. So now this last part is kind of putting everything together and applying our gas laws using stoichiometry from or the earlier chapters. So how can we apply gases to reactions, balanced reactions that use gases, that have gases in the balanced equation? And it's pretty straightforward because the ideal gas law gives us a way to calculate moles. There's an N component in PivNert, right? So if we know pressure, volume, and temperature of a sample, you can calculate what N is. And that N moles of a gas can be directly applied via stoichiometry into a balanced reaction. And it's the same mole to mole ratio that you've seen and used in balanced equations and stoichiometry before, right? So just remember, if we know P, V, and T, we can get N and use it in our stoichiometry. So I think it's just best to do questions, all right? So here's a question. Cl2O is used to kill bacteria in some water treatment plants. So small amounts of this gas can be produced in the laboratory with this reaction. All right, so there's the reaction, and it's balanced. So you need 15 liters of this gas at a temperature at 21 degrees and this pressure. You have an excess of SO2. What is the mass of chlorine gas that you need? So that's saying SO2 is in excess. So that right off the bat is saying SO2 isn't the limiting reagent, that it's going to be Cl2. Chlorine gas is what's going to be the limiting reagent. So that is what's going to determine how many moles of the product we make. So we are trying to make Cl2O gas. So these moles will be directly related to one another. So to get the moles of chlorine gas, it gives us its ideal gas law information. So it gives us volume, it gives us temperature, and it gives us pressure. So we can get N here. So PV equals nRT. So I'm essentially just applying, oh wait, no, hold on. We want to know how much chlorine we need, but we are starting with, so it says we want to make 15 liters of the product, and we need to back calculate how much of the reactant we need. Sorry about that. So, but still it works the same. So again, so PV equals nRT. The N that we get out of this will end up being moles of Cl2O. Right? So I'll just rearrange some stuff to make it nicer. So PV over RT. So now I just stick in the values that it gives us. So the number of moles of Cl2O will be equal to 0.981 atm, volume 15.0 liters over R, just leave that there. So T is 21 plus 273.15 Kelvin. All right, so N is equal to 0.6099, I think it's 3 sig figs, moles of what? Well, let's just say we want to make 15 liters of the Cl2O gas, so it's moles of Cl2O. The question says that we need mass of chlorine gas. So now we can just use regular stoichiometry. We've already done the ideal gas law part. We have moles of a gas. We have the moles of substance. It doesn't matter that it's a gas at this point. So let's take this value. So 0.6099 moles of Cl2O. So let's look at the stoichiometry here. So it looks like there's 1 mole of Cl2O for every 2 moles of chlorine gas. So I'm going to write here 1 mole of Cl2O gives you 2 moles of chlorine gas. All right? So if the question asked how many moles of chlorine gas you needed, then I'd stop right here. But it doesn't. It actually wants mass. So we need to do one step further and use molar mass. So 1 mole of Cl2 is equal to 70.9 grams of that gas, right? And then, and that's it. And so if you plug that into your calculator, you'll get an answer of 56 grams of chlorine is needed for this particular for this particular reaction in order to get a certain amount of product. So the only new thing was using PivNert with the information given to get number of moles of either a product or a reactant. That's the only new thing. So if you know PivNert and you know how to get number of moles, you're good. All right. So here is a slightly different question. So this question says ammonium perchlorate is used as a solid state rocket propellant. So I have the formula molecular mass here. So here is a reaction for rocket propellant. So it's 2 of the ammonium perchlorates gives you a mole of N2, a mole of Cl2, 2 oxygens, and 4 waters, all in the gas form. So we're going from 2 moles of solid to 1, 2, 3, 4, 5, 6, 7, 8. 8 moles of gas. So the question says, this is important because it says, what total volume of gas at 100 degrees Celsius and 1 atm can be produced from 100 kilograms of ammonium perchlorate? All right, so let's just think about this. So PV equals nRT. So I want to get volume. They told us temperature and pressure. Okay, so I need to get moles somehow to get volume of gas. These are the steps I think about. So where will I get moles of gas produced? So the only place that moles of gas are made are in the products. So if this reaction goes, I get 8 moles of gas produced. All right, so this is where now, so we're doing stoichiometry, but it's the other way, right? We're starting with stoichiometry and then using our ideal gas law. So let's start with our mass of ammonium perchlorate, convert that to moles, use our mole ratio in stoichiometry to say, okay, for every 2 moles of ammonium perchlorate, I produce, see now it doesn't care about what gas, so let's just consider it all together. For every 2 moles of ammonium perchlorate, I make 8 moles of gas. So we will use that conversion. So now I know how many moles of gas that we have. And remember how we said before, it doesn't matter how much the gas weighs or what the identity of the gas is, it just matters how many moles are present. So that's why we can just say, okay, 2 moles of ammonium perchlorate just make 8 moles of gas. And it doesn't matter what the actual identity is. That's why it's such a great rocket propellant, because 2 moles of the stuff can produce 4 times the number of moles of gas. All right, so let's do this. So I'm going to start. So I need to get moles of gas. That's like my goal. So I'm going to start with 100 kilograms of ammonium perchlorate. All right, and I want to get to moles, so I need to get out of kilograms. Don't want that. Want to be in grams. Okay, now I'm in grams. So now I can use the molecular weight that they gave us. So remember, the molecular weight is in grams per mole. So 1 mole of substance is equal to 117.49 grams. So now I'm in moles of NH4ClO4. So now that I'm in moles, I can now use stoichiometry. I can say, okay, for every 2 moles of ammonium perchlorate, I can make 8 moles of gas total, because I counted all of these up. I mean, you could do this for all of them singularly, but why would you want to do that? Because you're going to end up just adding them all up anyway, right? You could do this reaction and say, okay, for every 2 moles of ammonium perchlorate, I make 1 mole of nitrogen. Okay, now I have to do it again for making 1 mole of chlorine. Okay, I make 2 moles of oxygen. See, you can just add them up all right now. So the conversion I'm going to use is, nope, not 1, 2. 2 moles of NH4ClO4 is equal to 8 moles of gas. All right, and so if you do that, you make 3,404.5 moles of gas. Great. So this is our N component in our PivNert equation. Yay. So now we can use that. So remember, PV equals nRT, but we want V, right? What volume? Yep. So nRT over P. So N, we just got that. So 3,404.5 moles times R times temperature, which is 100 degrees. So pretty hot. I mean, it's pretty hot in a rocket, I'm assuming, especially near the, near the propellant and like the fire. So 100 plus 273.15, that's in Kelvin, over pressure, which is 1. Cool. So I think we're going to have 3, this looks like 3 sig figs. All right. And so, yeah, stick that into your calculator and you get that you make 1.04 times 10 to the 5 liters. So that's a lot of volume of gas from a solid source. That's the important thing here when it comes to rocket fuel and rocket propellants. All right. So those are this video kind of showcased a lot of different ways we can use and interact with the ideal gas law and how we can apply it to different types of questions that I could ask you. All right, so stick around for the next maybe 1 or 2 lecture videos, and I'll talk more about real gases and the behaviors of gases on a molecular level.